Hi there, this is Lucius Laframboise from ENG Suite. And today we are going to continue talking about normality testing by learning about the Royston expanded Shapiro-Wilk test. So last week you may remember that we took a look at the Shapiro-Wilk test, but it only calculates for sample sizes up to 50. As engineers, that's generally going to be enough, but sometimes we have to do more than 50, and with the power of the Shapiro-Wilk test, which we'll get into later, it is very helpful to have this Royston expanded, because the Royston expanded Shapiro-Wilk test is an approximation of the Shapiro-Wilk test that increases the sample size up to 5,000 samples. Now, as an engineer, I truly hope that you don't have any more than 5,000 samples, because if it fails for normality, that's going to be expensive to remeasure, and it probably was the first time around. Okay, so just like the Shapiro-Wilk test, because the Shapiro-Wilk test and the Royston expanded are basically the same test, the Royston expanded is just a different way of calculating and approximating that W test statistic. They both have the same null and alternative hypothesis, which is the same as all of the other normality tests that we have seen so far. The null hypothesis being the data follow a normal distribution, and the alternative being that the data do not follow a normal distribution. So how does it work? Well, the Royston Shapiro-Wilk test algorithmically determines the constants instead of using a table to calculate them. So if you remember in the Shapiro-Wilk test, we had a giant table of constants that we then had to use the sample size in order to figure out what those constants are going to be and the actual placement in the equation. Well, the Royston Shapiro-Wilk test simplifies it down a ton, so instead of needing an enormous 5,000 by 2,500 table of values, we use an algorithm to approximate those coefficients. And due to the approximation method of those coefficients, instead of having to calculate a bunch of individual values, we can just use a correlation coefficient between the ordered data and these constants to calculate that approximated W test statistic. So let's actually see that in math. Well, W, our approximated Shapiro-Wilk test statistic, equals the correlation of yi, our ordered data, and ai, the Royston constants in order, and then we square that correlation. So that W test statistic is pretty easy to calculate once we get all of our a values. To calculate the a values, we're going to have to use this piecewise function. And to start, we'll have to take the nth term of the sorted data. So that means that we are actually working backwards from the highest, the greatest value, and then sort of filtering down to the lowest, which is kind of non-intuitive since all of our other normality tests we've looked at, we sort everything in ascending and we sort of start from the lowest. In this case, we'll still do something very similar. So an is this really long equation that relies heavily on this u variable. And u, you'll see down here, is actually a constant based on our sample size n. So u equals 1 over the square root of n. That makes this pretty easy, just some big coefficients we have to deal with. And then you'll see at the end, we're adding on this term here, mn over the square root of capital N. So mi is our normal score. Now, you may remember from our Ryan-Joyner test that we use this normal score. The normal score is calculated down here, norm.s.inv of I minus 0.375 over n plus 0.25. If you're curious to learn more about what this normal score is, please check out that Ryan-Joyner test. That will go into the definition of normal score and what this is. We're not going to go into that today because we still have plenty of equations to get through. But this capital M value is just the sum of the squares of all of our mi values. Once we have those, we can also do a of n minus 1, which is a very similar equation, just some different coefficients, and we, at the end, take mn minus 1 instead of mn. Then we can jump back to the beginning, because a1 equals negative an, and a2 equals negative an minus 1. Then, for everything in between, we can use ai, where ai equals mi over the square root of epsilon. So mi, again, the normal score for that value. Epsilon is reliant again on an and an minus 1, because the equation for this is the numerator being m minus 2mn squared minus 2mn minus 1 squared over 1 minus 2an squared minus 2an minus 1 squared. So none of this is too terrible, especially in Excel. It's a lot easier than using tables, and that is one of the reasons why the Royston Shapiro-Wilk test can be great for engineers. So then we would take this array of AI values, we would get the correlation coefficient with our ordered data, and then we would square that for the W test statistic. But once we have the W test statistic, we want to convert it into a p-value, which can help us assess our hypotheses. So if you remember from the Shapiro-Wilk test video that we did, there's two methods of calculating the associated p-value that are often used. The first is the Shapiro-Wilk p-value table, which we used last time, and if you remember, only goes up to 50 samples, which means we will need the second one today, using the 1's complement of W and the derived mu and sigma to calculate the p-value associated from the normal CDF. We'll get into that in a sec. Just something to note, though, is that some statistical packages will use method 2. However, method 2 is generally reserved for the Royston expanded version of the Shapiro-Wilk test. However, there are some important power considerations we will get to in a later video based on new research about the Shapiro-Wilk tests and its approximations and their relationships. That is for a later date. Today we are using method number 2. So calculating the associated p-value relies on that mu and sigma. Mu and sigma are constants based on the sample size. So they're pretty simple equations. Again, just really long coefficients. We then use that mu and sigma to calculate a z-score from the natural log of 1 minus w. That z-score is then used to find the left-tailed probability of that value of z from the standard normal distribution. Then, because we already took a 1 minus here and we're calculating a left-tailed, we want to take 1 minus that again to get our right-tailed probability. So we have our Shapiro-Wilk statistic, we have our p-value. How do we do this? What do they mean? Well, the Shapiro-Wilk test statistic, again, this is an approximation, but it behaves the same way that the Shapiro-Wilk does. So the Royston Shapiro-Wilk and the Shapiro-Wilk, higher values correspond to a higher probability that the data originated from the normal distribution. That's awesome, just like the Shapiro-Wilk test. The p-value, just like all of our other p-values, we're going to use a critical value. That critical value is generally going to be 0.05, but make sure to check with your organization. Make sure you're using the correct critical value for your organization. All right, we got through all of the concepts. We took a look at the math. Let's actually do it in Excel. All right, here we are in Excel, and we are ready to get started. My workbook is already set up. I've got some data. I've got a lot of formatting in, mean, standard deviation, and our sample count. I highly recommend that you download this workbook. Link in the description. Go ahead, download that. It's going to make your life a whole lot easier, and the math will already be done, so if you want to use it, go ahead. Or if you want to follow along, just delete a little bit of the data and work right alongside of me. So the first thing we're going to start with is sorting our data. And we're going to sort in ascending order, and we're just going to take that whole data column, and there we go, everything's sorted. Next, we're going to need this MI, this normal score. So pretty easy to calculate this. We'll do norm.s.inv, and then our probability is going to be I minus 0.375 divided by n, and then we're going to absolute reference that, plus 0.25, okay? So there we go, and let's double click to fill all the way down. So the next thing that we're going to calculate is our AI column, and AI is a piecewise function that starts with an. So we're going to actually have to start all the way down at the bottom, and everything else is pretty contingent on that. So because of that, this workbook that we made only works for samples of 30. So if you have a sample size that's below 30 or above 30, this won't work. If you want to use samples that are a different size, I highly recommend using QE Suite. QE Suite is a great add-in that performs all of this math for you every time super easily. There's a link in the description and in the cards that will show you how to get your free trial started in just a few minutes. Super easy. I highly recommend it. Let me show you just how quick it is. So to do the Royston, you would just do QE.Royston Shapiro-Wilk. Select your data, and I'm going to hide my QQ plot. And look at that, just like that, we already have our Royston Shapiro-Wilk. Super cool. Okay, so you're here to learn the math. Let's get back to it. So like I said, we're starting with AN, and this is kind of a pain equation, but we need a couple things first. So the first thing that we're going to need is U. If you remember from the PowerPoint, U is just 1 over the square root of N. Yes, awesome. We're also going to need that capital M. Capital M is the sum squared of our MI values. So we take that. Awesome. We have M, we have U, we have MN. Let's get started. So AN equals negative 2.706056 times power of U. So we raise that to the 5th. And now we're going to say plus 4.434685 times power, and I'll just do L3, which is U, to the 4th, minus 2.07119 times power of L3, again that's U, to the 3rd, minus 0.47981 times power of L3 squared. Then we're going to add 0.221157 times L3, which is U. And then we're going to add our MN divided by the square root of capital M. Enter. All right, there we go. We have our AN minus 1 value. Now let's do A of N minus 1, which is negative 3.582633 times power. Again, that's going to be L3 to the 5th plus 5.68263 times power of L3 to the 4th minus 1.752461 times power L3 to the 3rd minus 0.293762 times power of L3 squared plus 0.042981 times L3. And this time our final term is going to be M of N minus 1 divided by square root of, we're going to do L2 because we know that is our capital M value. And there we go. Okay, so now that we have AN and AN minus 1, we can do A of 1, which is just negative AN. Then we're going to do negative AN minus 1 to get A2. Okay, so now to get everything in between, our equation is AI equals MI over square root of epsilon. So that's this E here. We need to calculate epsilon. Now I have it broken up into a numerator and denominator just to make things a little bit easier. So we'll start with the numerator. And the numerator is capital M minus 2 times the power of MN squared minus 2 times the power of MN minus 1 squared. Enter. And then our denominator is very similar. It's 1 minus AN minus 1 minus 2 times the power of AN squared minus 2 times the power of AN minus 1 squared. Enter. And then we just take our numerator divided by our denominator to give us epsilon. Then AI is pretty easy. It's just going to be MI divided by the square root of epsilon, absolute reference with F4, and enter. Now I'm going to double click, and that's going to fill us all the way down there. Wonderful. There we go. So now that we have our AI column, we can calculate our W test statistic by taking, and I'm going to first do power of choral of yi and ai. Close that parentheses, raise it to the power of 2, enter, and there we go. 0.9571, which is exactly what we got from QE Suite. So how do we turn that into a p-value? Well, we're going to first have to derive this mu and sigma to get z. So mu is going to be equals 0.0038915 times the natural log, and here we'll actually power of the natural log of n cubed minus 0.083751 times power natural log of n squared minus 0.31082 times the natural log of n minus 1.5861. Awesome, there's our mu, and now we're going to do sigma. Sigma equals exp of 0.0030302 times power natural log of n squared. Then minus 0.082676 times, got it. Okay, let's double check. So exp 0.0038, wrong one. 0.0030302 power ln n squared minus 0.082676 times natural log of n minus 0.4803. Yep, I'll accept that. And now we have mu and sigma. Let's calculate our z value. So our z value is going to be the natural log of 1 minus w minus mu divided by sigma. There we have a z value between 0 and 1. Wonderful. So our p-value is 1 minus norm dot s dot dist of that z value, true. Look at that, 0.260695, just like what we got in QE Suite. Well, that's it for the Royston Shapiro-Wilk test. Reminder, this works all the way up to 5,000 samples unless you're using this workbook. This workbook can only handle exactly 30. QE Suite is going to be a great solution. Make sure to go get started on your 2-month free trial. Go check out some of these other videos. We have a lot of great resources on engineering statistics. Please let us know if you got any questions on any of it. We'd love to help. So thank you so much for watching. Have a great day, and please do something awesome.